This is Sleepy Space, a slow space story to help you fall asleep. Look up on a clear night, far from city lights, and the universe appears still. The stars hang motionless against the dark. The moon follows its familiar path. The planets hold their positions, steady and unchanging. It looks like a photograph, but it isn't. That sense of stillness is one of the most convincing illusions the universe produces. Every point of light you see is moving, not slowly, not gently. It is moving through space at speeds that defy ordinary understanding. The stars are orbiting the center of the galaxy. The galaxy itself is spinning. And beyond our own island of stars, distant galaxies are racing away from us, carried into deeper space by something we cannot see and do not fully understand. The universe is not a static picture. It is a single frame from an unimaginably long film. And the film has never paused. For most of human history, we believe the cosmos was eternal and unchanging. The stars felt permanent. The sky felt fixed. Even when we learned that Earth moved around the sun, the universe beyond still seemed calm, stable, settled into its arrangement. That belief lasted until the early 20th century. In the 1920s, an astronomer named Edwin Hubble began studying the light from distant galaxies. He wasn't looking for motion, he was measuring distance. But hidden in the data was something strange. The light from these galaxies was shifted toward the red end of the spectrum. This shift, called redshift, revealed motion. Not motion through space, but motion of space itself. The farther away a galaxy was, the more its light was stretched. The more space lay between us and that galaxy, the faster it appeared to be receding. It was as if the universe was expanding in every direction at once. Everything was moving away from everything else. This was not what scientists expected. Even Albert Einstein had assumed the universe was static when he first wrote his equations of general relativity. To preserve that stillness, he introduced a mathematical term designed to counteract gravity and prevent motion on the largest scales. When Einstein learned of Hubble's observations, he reportedly called that addition his greatest mistake. Because the universe was not standing still. And it never had been. At first, it was tempting to imagine galaxies flying outward through space, like debris from an explosion. But that picture is misleading. The galaxies are not simply traveling away from us. Space itself is expanding between them. A common analogy is a balloon with dots painted on its surface. As the balloon inflates, the dots move farther apart, not because they are sliding across the surface, but because the surface itself is stretching. In our universe, galaxies are like those dots. Space is the balloon. This expansion happens everywhere, all at once. We can measure its rate. We call it the Hubble constant. Roughly speaking, for every 3 million light-years of distance, space expands fast enough to add about 70 kilometers per second to a galaxy's recession speed. The farther away something is, the faster it recedes. There is no special center, no privileged location. Every observer sees the same pattern. But for decades, scientists believed this expansion was slowing down. Gravity pulls matter together. Over time, the attraction of all the mass in the universe should gradually decelerate the expansion that began with the Big Bang. That expectation was reasonable. It was also wrong. In the late 1990s, two independent teams of astronomers were studying extremely distant Type 1, a supernovae, exploding stars that serve as reliable distance markers. These stellar explosions have a predictable brightness, making them powerful tools for mapping the universe. The results were shocking. The supernovae were dimmer than expected, farther away than they should have been if the universe were slowing down. The expansion was not decelerating, it was accelerating. Something was pushing against gravity. Something was driving space itself to stretch faster and faster over time. The force was invisible, its nature unknown, its presence undeniable. We gave it a name: dark energy. The name does not explain it. It merely labels our ignorance. Dark energy appears to make up nearly 70% of everything in the universe. It permeates space itself, exerting a kind of negative pressure that overwhelms gravity on the largest scales. Unlike matter, which becomes more dilute as space expands, dark energy maintains a constant density. As space grows, more dark energy appears with it. The universe does not merely expand, it accelerates. Every distant galaxy is moving away from us faster today than it was yesterday, faster tomorrow than it is today. Regions of space that are not gravitationally bound will eventually slip beyond our reach, disappearing from view forever. The still night sky hides this reality well. The stars look fixed, the galaxies look calm. But beneath that calm lies motion without rest. To understand where the universe is headed, we must understand how it began. Because the future of the cosmos is written into its first moments, encoded in the expansion that started everything and never stopped. The universe began not as an explosion in space, but as the expansion of space itself. There was no empty void that suddenly filled with matter and energy. There was no surrounding darkness into which the universe burst. Space and time came into being together and immediately began to grow. We call this beginning the Big Bang, though the name is somewhat misleading. There was no bang, no sound, no explosion in any conventional sense. What happened was more fundamental. The entire fabric of existence began to stretch, and everything we know emerged from that stretching. In the first, unimaginably brief fraction of a second, the universe underwent a period of exponential expansion called inflation. Space grew faster than the speed of light, doubling in size over and over in intervals almost too short to measure. A region smaller than an atom swelled to larger than a galaxy in less time than it takes light to cross the nucleus of a single atom. This inflationary burst smoothed out the universe, spreading matter and energy evenly across vast distances. It explains why, when we look in any direction, the cosmos appears roughly the same. The temperature, the density, the distribution of galaxies, all remarkably uniform because everything we can see originated from a tiny patch that inflation stretched to cosmic proportions. When inflation ended, the universe was filled with an incredibly hot, dense soup of fundamental particles and energy. Quarks and electrons existed but couldn't yet form stable atoms. The temperature was trillions of degrees, far hotter than the core of any star. Photons scattered constantly off the charged particles, unable to travel more than a tiny distance before colliding with something else. As space continued to expand, this primordial plasma cooled. Within the first few minutes, protons and neutrons combined to form the nuclei of the lightest elements: hydrogen, helium, and trace amounts of lithium. But the universe was still too hot for electrons to settle into orbit around these nuclei. It remained opaque, a glowing fog through which light could not freely travel. This state persisted for roughly 380,000 years. Then, as expansion continued and temperature dropped, electrons finally combined with nuclei to form complete atoms. This moment, called recombination, changed everything. With charged particles bound into neutral atoms, photons could suddenly travel freely through space. The universe became transparent. The light released at that moment is still traveling through space today. We detect it as the cosmic microwave background, a faint glow coming from every direction in the sky. This radiation has been stretched by the expansion of space, shifted from visible light down to microwave wavelengths. But it remains a photograph of the universe as it appeared just a few 100,000 years after the beginning. The cosmic microwave background is remarkably smooth, uniform to better than 1 part in 100,000. But tiny variations exist, regions slightly warmer or cooler than average. These variations represented subtle differences in density, places where matter was slightly more or less concentrated. And these differences mattered. Gravity amplified the variations. Regions with slightly more matter attracted even more matter. Over millions of years, these denser regions grew, pulling in surrounding gas through gravitational attraction. Eventually, the first stars ignited within these gathering clouds. Galaxies formed, clusters of galaxies assembled. The structure we see in today's universe grew from those tiny fluctuations imprinted in the first moments of existence. The initial conditions set during the Big Bang and inflation determined everything that followed: the strength of the fundamental forces, the types of particles that existed, the rate of expansion, the distribution of matter and energy, all established in that first instant. The universe began with a particular set of properties, and those properties shaped its entire evolution. One might expect that after such a violent beginning, the expansion would gradually wind down. The momentum from the Big Bang should carry things outward for a while, but gravity, always attractive, should eventually slow the recession. For billions of years, this is exactly what happened. Gravity fought against expansion from the very beginning. Every particle of matter attracted every other particle. As space grew and matter spread out, this gravitational attraction worked to pull everything back together, to reverse the expansion, to collapse the universe back into the dense state from which it emerged. For much of cosmic history, gravity was winning, in a sense. The expansion continued, but it was slowing down. The rate at which space grew was decreasing over time, pulled back by the cumulative gravitational attraction of all the matter in the universe. Imagine throwing a ball upward from Earth's surface. The ball moves away from the ground, but Earth's gravity pulls it back, slowing it down. If you don't throw it fast enough, it eventually stops and falls back. If you throw it hard enough, it escapes, but even then, gravity continues to slow it, making its upward journey ever more gradual. For billions of years, the universe seemed to be following a similar pattern. Space was expanding, but the expansion was decelerating. Whether it would expand forever or eventually collapse depended on how much matter existed, how strong gravity's pull was compared to the outward momentum. Cosmologists spent decades trying to measure this deceleration, to determine the universe's fate by measuring how much the expansion had slowed over cosmic time. They expected to find a universe gradually losing speed, its expansion breaking under gravity's influence. For half the universe's lifetime, roughly the first 7 billion years, gravity pulled back against expansion, slowing it down. But then, something unexpected happened, something that would change the fate of everything. In the late 1990s, two independent teams of astronomers set out to measure how much the universe's expansion had slowed since the Big Bang. They used some of the most distant supernovae ever observed, stellar explosions so far away that their light had traveled for billions of years before reaching Earth. The method was elegant. Type 1. A supernovae explode with a characteristic brightness. By measuring how bright they appear from Earth and comparing that to their actual luminosity, astronomers can calculate their distance with precision. By measuring their redshift, they can determine how fast they're receding. Plot distance against recession velocity for many supernovae, and you can trace the expansion history of the universe. Both teams expected to find the same thing: a universe gradually slowing down. The question wasn't whether expansion was decelerating, but how much. Would it slow enough to eventually collapse, or would it coast outward forever, gradually approaching a standstill? What they found was neither. The distant supernovae were dimmer than expected. Not by much, but consistently, measurably dimmer. This dimness meant they were farther away than they should have been in a universe where expansion was slowing down. If the expansion had been decelerating as predicted, these ancient explosions should appear closer and brighter. There was only one explanation that fit the data. The expansion wasn't slowing, it was speeding up. The initial reaction was disbelief. Teams checked and rechecked their measurements. They looked for errors in their methods, problems with their instruments, alternative explanations for the dimness. Perhaps dust between us and the supernovae was absorbing light, making them appear fainter. Perhaps these ancient explosions weren't quite as uniform as thought, varying in brightness in ways that mimicked greater distance. But every test confirmed the original finding. The supernovae really were farther away than expected. The universe really was accelerating. This discovery contradicted fundamental assumptions about how the cosmos should behave. Gravity attracts. It pulls things together. It should slow expansion, not accelerate it. Yet here was clear evidence that something was overpowering gravity on cosmic scales, pushing space to expand faster and faster. The teams published their results in 1998. The astronomy community reacted with a mixture of excitement and skepticism. There was, if true, one of the most important discoveries in the history of cosmology. But it was also profoundly strange, requiring something entirely new in our understanding of the universe. Further observations only strengthened the case. More distant supernovae showed the same pattern. Different methods of measuring cosmic expansion confirmed the acceleration. Within a few years, the evidence became overwhelming. The universe was indeed speeding up, and had been for roughly the past 5 billion years. We needed a name for whatever was causing this acceleration. We called it dark energy. a placeholder term that acknowledges our profound ignorance about its true nature. The name tells us almost nothing about what it actually is, only what it does. It's dark because it doesn't emit, absorb, or reflect light. It's energy because it has to contribute to the total energy content of the universe to drive expansion. And it's everywhere. Current measurements suggest dark energy comprises roughly 68% of all the energy in the universe. Matter, both the ordinary kind that makes up stars and planets and the invisible dark matter that dominates galactic halos, accounts for only about 32%. The universe is dominated by something we don't understand, something whose very existence was unknown until recently. Dark energy has a peculiar property that sets it apart from matter and ordinary energy. As the universe expands and space grows, matter spreads out and becomes less dense. The same number of particles occupy a larger volume, so the density decreases. But dark energy doesn't dilute. Its density remains constant even as space expands. This means that as the universe grows, more dark energy comes into existence. Not in the sense that it's created from nothing, but that the total amount of dark energy increases as the total volume of space increases. Every cubic meter of space contains the same amount of dark energy, regardless of how much space there is. This constant density creates a kind of negative pressure, a repulsive effect that pushes space to expand. Unlike gravity, which pulls things together and strengthens when things are close, dark energy's influence grows as the universe grows. More space means more dark energy, which means stronger acceleration. For the first several billion years after the Big Bang, matter dominated the universe. There was enough gravitational attraction from all the matter to overpower dark energy's influence. Expansion continued, but it was slowing down just as expected. But as space expanded, matter thinned out while dark energy maintained constant density. Eventually, around 5 billion years ago, dark energy overtook matter as the dominant influence on cosmic expansion. From that point forward, the universe began to accelerate. We can measure dark energy's effects with increasing precision. Observations of the cosmic microwave background, the large-scale distribution of galaxies, the brightness and redshift of distant supernovae. All these independent lines of evidence point to the same conclusion. Dark energy is real. It dominates the universe, and it's driving space to expand at an accelerating rate. Yet we still don't know what it is. The most straightforward explanation is that it represents the energy of empty space itself, a property sometimes called the cosmological constant. Einstein's equations allow for such a term, a constant energy density inherent to the vacuum. But attempts to calculate what this vacuum energy should be yield results that are spectacularly wrong, off by more than 100 orders of magnitude. Other possibilities exist. Perhaps dark energy isn't constant but changes over time. Perhaps it's a new field permeating space, something like the Higgs field, but with different properties. Perhaps it's a sign that our understanding of gravity breaks down on cosmic scales, and the acceleration is telling us that Einstein's equations need modification. We don't know. We can measure dark energy's effects, map its influence across the cosmos, trace its impact on the universe's evolution, but its fundamental nature remains mysterious. What we do know is that dark energy doesn't just influence the universe's expansion. It determines the ultimate fate of everything that exists. And that fate depends on a delicate balance of cosmic forces. The fate of the universe comes down to a competition between forces. On one side, gravity, pulling everything together. On the other, dark energy, pushing space apart. The balance between these influences determines not just how the universe expands, but what it will ultimately become. This balance depends on something called cosmic density. Add up all the matter and energy in the universe, divide by the total volume, and you get an average density. This number, seemingly simple, holds enormous power over cosmic destiny. There exists a special value called the critical density. If the actual density of the universe equals this critical value, space is flat in the geometric sense. If the density is higher, space curves back on itself, forming a closed geometry. If the density is lower, space curves outward, creating an open geometry. These three possibilities, closed, flat, and open, each lead to different fates. In a closed universe with density above critical, gravity eventually wins. The expansion slows, stops, and reverses. Space begins to contract. Galaxies that are now receding would begin to approach. The cosmic microwave background would shift from red to blue. Everything would fall back together, collapsing into a state of increasing density and temperature, a mirror image of the Big Bang, sometimes called the Big Crunch. In an open universe with density below critical, expansion continues forever. Space keeps growing, thinning out, cooling down. Gravity never gains enough strength to halt the expansion. The universe spreads out endlessly, structures becoming increasingly isolated as distances grow without bound. In a flat universe right at critical density, the outcome depends on other factors. Without dark energy, a flat universe would expand forever, but gradually slow, approaching a standstill without ever quite reaching it. With dark energy, flatness doesn't prevent acceleration. For decades, cosmologists worked to measure the universe's geometry by determining its density. The task was challenging. Most matter in the universe is dark, invisible except through its gravitational effects. Measuring the total mass of galaxies, clusters, and vast cosmic structures required careful observation and clever techniques. Early measurements suggested the density was below critical. The visible matter and even the invisible dark matter together didn't add up to enough mass to make the universe flat. This implied an open geometry, a universe destined to expand forever. But these measurements didn't account for dark energy. When dark energy was discovered and its contribution to the total energy budget was calculated, the picture changed completely. Current observations indicate the universe is remarkably flat. Not perfectly flat, but close enough that we can't measure any curvature. The total density, including matter and dark energy, sits right at the critical value within measurement uncertainty. This flatness is actually surprising. For the universe to remain nearly flat for billions of years, it must have been extraordinarily flat in the beginning. Even tiny deviations from flatness early on would have been amplified over time. That we observe such precise flatness today suggests inflation in the first moments of the Big Bang stretched space so thoroughly that any initial curvature was smoothed away to imperceptible levels. But knowing the geometry isn't enough to predict the future. We also need to understand how dark energy behaves over time. Does its density truly remain constant, or does it change as the universe ages? Physicists describe dark energy's behavior using something called the equation of state parameter, often written as W. This parameter relates dark energy's pressure to its density. For a true cosmological constant, W equals -1. The density stays constant as space expands, but W could have other values. If W is greater than -1, dark energy weakens over time. Its influence diminishes as the universe ages, and eventually gravity might overcome it, potentially leading to collapse. If W is less than -1, dark energy strengthens over time. Its influence grows, leading to faster and faster acceleration. Current measurements place W very close to -1. Dark energy appears to behave like a cosmological constant, maintaining steady density as space grows. But the measurements have uncertainties. We can't completely rule out small deviations from -1. These subtle differences matter enormously. If W is even slightly less than -1, the universe faces a dramatically different fate than if W equals -1 exactly. Small numbers in fundamental physics often have profound consequences. The strength of dark energy relative to matter also evolves. In the early universe, matter dominated. Gravity was the controlling force, shaping the formation of structures, governing how things moved and interacted. Dark energy existed but contributed little to the overall dynamics. As the universe expanded, matter thinned while dark energy maintained constant density. Around 5 billion years ago, the two reached equal influence. From that point forward, dark energy has dominated, and its dominance grows stronger with each passing billion years. Today, dark energy outweighs matter by more than 2 to 1. In the future, this ratio will continue to shift. Matter becomes increasingly dilute, while dark energy density remains steady. Eventually, dark energy will dominate so completely that matter's influence becomes negligible on cosmic scales. This doesn't mean matter disappears. Locally, within galaxies and clusters held together by their own gravity, matter still dominates. But on larger scales, across the vast spaces between galaxy clusters, dark energy controls the dynamics. We measure these cosmic parameters with increasing precision. Satellites map the cosmic microwave background with extraordinary detail. Telescopes survey millions of galaxies across cosmic history. Supernovae at various distances provide snapshots of expansion at different epochs. Each observation refines our understanding of the universe's composition and geometry. The current best measurements tell us the universe is flat, dominated by dark energy behaving like a cosmological constant and accelerating at an increasing rate. If these measurements hold, if dark energy truly remains constant, the future is mapped out with reasonable confidence. With dark energy in command and the universe flat and accelerating, we can now trace the path ahead, a journey that stretches beyond comprehension into the deep future. The universe today is filled with structure. Galaxies gather into groups and clusters. Clusters connect through vast filaments of matter, creating a cosmic web that spans hundreds of millions of light years. Between these filaments lie enormous voids, regions of space nearly empty of galaxies. This web represents the large-scale organization of the cosmos. It formed over billions of years as gravity pulled matter together, drawing galaxies along invisible threads toward dense nodes where clusters grew. The pattern we see reflects the tiny density variations imprinted in the first moments after the Big Bang, amplified over cosmic time into the structures we observe today. But this web is not permanent. Acceleration is slowly tearing it apart. Not all structures will separate. Gravity holds some regions together strongly enough to resist the expansion of space. Our own galaxy, the Milky Way, is bound by its own gravity. The Andromeda Galaxy, though currently approaching us, is part of the same gravitationally bound system. Together with dozens of smaller galaxies, we form what's called the local group, a collection spanning several million light-years. The local group is bound. Its members orbit a common center of mass, held together by mutual gravitational attraction. The expansion of space affects the vast distances between galaxy groups, but within a bound group, gravity dominates. The local group will not expand. Its galaxies will continue to orbit, interact, and eventually merge. In fact, the Milky Way and Andromeda are on a collision course. In roughly 4 billion years, they'll begin to merge, their stars intermixing as the two galaxies spiral together over hundreds of millions of years. Eventually, they'll form a single large elliptical galaxy, a quiet retirement for both spirals. But beyond the local group, the situation changes. The nearest large cluster, the Virgo cluster, sits about 50 million light-years away. That distance is growing. The space between us and Virgo is expanding, and the rate of expansion is accelerating. Currently, we can still see Virgo. We can observe its galaxies, study their properties, measure their distances. But as acceleration continues, Virgo will recede faster and faster. Eventually, it will recede so quickly that light from Virgo can no longer reach us. The cluster will cross what's called the cosmic event horizon, the boundary beyond which recession velocity exceeds the speed of light. This doesn't violate relativity. Nothing is moving through space faster than light, but space itself can expand at any rate. As the distance grows, the expansion rate across that distance can exceed the speed that light can travel through expanding space. Once Virgo crosses this horizon, it disappears from view permanently. Light emitted from Virgo will struggle against the expansion, but never make progress toward us. The cluster becomes causally disconnected beyond our ability to observe or influence. This pattern will repeat across the cosmos. Distant galaxy clusters currently visible at the edges of our observable universe will fade from view first. Their light will redshift toward longer and longer wavelengths, becoming dimmer and dimmer until it vanishes entirely. Closer structures will follow. The Great Coma Cluster, the vast superclusters that organize the cosmic web, even relatively nearby groups, all will eventually recede beyond the horizon. One by one, the galaxies outside our local gravitationally bound region will slip away. The timescale for this isolation spans tens of billions of years. 100 billion years from now, perhaps longer, observers in what remains of the local group will look out and see almost nothing beyond their own merged galaxy. The cosmic web, the clusters, the billions of galaxies currently visible, all will have receded beyond reach. The cosmic microwave background will disappear as well. This ancient light, already redshifted from visible wavelengths down to microwaves, will continue to shift toward longer wavelengths. The photons will spread farther apart as space expands. their energy will diminish. Eventually, the cosmic microwave background will redshift into radio wavelengths, then into wavelengths so long and so sparse that detecting them becomes impossible. Future astronomers in this isolated galaxy will face a profound limitation. They won't see the Big Bang's afterglow. They won't observe the expansion of space carrying distant galaxies away. They'll inhabit a single large galaxy surrounded by darkness, with no direct evidence of the broader universe beyond. They might deduce the truth through theoretical reasoning. They could study stellar evolution, measure the abundance of light elements, develop cosmological models that predict a beginning. But they would lack the observational confirmation we enjoy today. The universe would hide its own history from them. The observable universe, from their perspective, will have shrunk to just the local group's merged remnant. Everything else will lie beyond an impassable horizon, receding faster than light can travel through expanding space. The cosmos will effectively contract around them, not because space is collapsing, but because acceleration pushes everything else away so quickly that light can no longer bridge the gap. This isolation is not destruction. The galaxies that cross the horizon continue to exist. They don't vanish from reality, only from visibility. Somewhere far away, they persist, perhaps themselves merged into single large galaxies, themselves surrounded by darkness, themselves isolated by acceleration. The universe becomes fragmented, not into separate universes, but into causally disconnected regions. Each island of gravitationally bound matter exists within its own horizon, unable to see or interact with the others. The cosmic web dissolves into isolated nodes, archipelagos of galaxies scattered across an expanding ocean of space. This represents just the beginning of what acceleration brings. The progressive isolation of structures, the shrinking of the observable universe to a local bubble. These changes set the stage for transformations far more profound. But this isolation is just the beginning. The universe's acceleration ensures that what comes next will reshape reality in ways both strange and inevitable. The isolation of galaxy groups marks only the first chapter in a future that extends far beyond human imagination. To understand what comes next, we must follow the timeline forward through eras measured not in billions of years, but in trillions, and eventually in numbers so large, they lose ordinary meaning. The universe is currently in what cosmologists call the stelliferous era, the age of stars. Stars shine in billions of galaxies. They fuse hydrogen into helium, helium into heavier elements, releasing energy that lights up space. This era has lasted roughly 14 billion years so far, but it won't last forever. Stars form from clouds of gas, primarily hydrogen. Each generation of stars converts some of that hydrogen into heavier elements. When massive stars explode as supernovae, they scatter these elements into space, enriching the gas clouds from which new stars form. But with each cycle, the available hydrogen diminishes. In 1 trillion years, perhaps 2 trillion, the last stars will form. The galaxies will have exhausted their reserves of raw material. Gas clouds will have been consumed, blown away, or locked into stellar remnants. No new stars will ignite. The universe will begin a slow fade. The stars that exist will continue burning until their fuel runs out. Small stars, red dwarfs much dimmer and cooler than our sun, can burn for trillions of years on their meager reserves. They'll be the last lights in the cosmos, faint embers glowing in an increasingly dark expanse. Eventually, even these will exhaust their fuel and fade. When the last star dies, the stelliferous era ends. The universe enters what's called the degenerate era, named for the degenerate matter that comprises stellar remnants, white dwarfs, the cooling cores of sun-like stars, neutron stars, the collapsed remains of massive stellar explosions, black holes of various sizes. These objects become the primary inhabitants of space. The timescale for the degenerate era is almost incomprehensible. It begins around 1 trillion years from now and extends perhaps 100,000 trillion years beyond that. During this vast span, the stellar remnants gradually cool. White dwarfs, initially hot enough to glow, radiate away their residual heat over trillions of years, eventually becoming cold black dwarfs, dark spheres of degenerate matter at the ambient temperature of space. But even matter itself may not be permanent. Some theories predict that protons, the building blocks of atomic nuclei, eventually decay. Not quickly, but over timescales so long that the current age of the universe represents less than a blink. If protons decay, the timescale for their half-life is at least 10 to the 34 years, possibly much longer. This means that after this unimaginable span, half of the protons in any given collection will have decayed into lighter particles, primarily positrons and photons. White dwarfs and neutron stars composed of protons and neutrons would slowly evaporate as their constituent particles decay. Over time periods that dwarf even the degenerate era's vast length, these remnants would dissolve, their mass converting into radiation and lightweight particles that quickly scatter into the void. Eventually, if proton decay occurs, only black holes would remain. Everything else, all the matter that once formed stars and planets and galaxies, would have decayed away. The universe would enter the black hole era. Black holes seem permanent, but they're not. In the 1970s, Stephen Hawking demonstrated that black holes emit radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to lose mass over time. The rate of mass loss is incredibly slow, especially for large black holes. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate completely. Supermassive black holes, millions or billions of times more massive, take correspondingly longer. But given enough time, even the largest black holes evaporate. The universe has nothing but time. After periods measured in 10 to the 100 years, even supermassive black holes dissolve into radiation. The final black hole emits a last burst of particles and vanishes, leaving behind only photons and a few lightweight particles expanding into the void. After the last black hole evaporates, the universe enters its final era, the dark era. No stars, no remnants, no black holes. Just photons and lightweight particles like electrons, positrons, and neutrinos scattered across space that continues to expand. The density of matter and energy becomes almost nothing. Particles are separated by distances so vast that they may never encounter anything else for the remainder of time. The universe approaches a state of maximum entropy, where energy is spread so evenly that no processes can occur, no structures can form, no changes can happen. This is sometimes called heat death, though the universe is anything but hot. Temperatures approach absolute zero. Energy differences, the driving force behind all processes, diminish to nearly nothing. The universe becomes cold, dark, and still. The timescale for reaching this state is nearly infinite. The dark era extends essentially forever, a static emptiness that persists without end. All the complexity, all the structure, all the energy that existed in the early universe has been diluted across such vast expanses that nothing remains but the faintest echo. Particles too sparse and too cold to interact. This seems like an absolute ending. The universe runs down completely, achieving a state of perfect equilibrium from which nothing more can emerge. The mathematics of thermodynamics and general relativity point toward this conclusion with seeming certainty. Yet even here, at the edge of comprehension, mysteries remain. Questions that hint at possibilities beyond heat death. The future we have traced seems inevitable, written into the mathematics of expansion and entropy. But our confidence in this ending rests on assumptions, and assumptions can be wrong. We assume dark energy remains constant, maintaining the same density as space expands. But we don't know if this assumption holds. Dark energy could change over time in ways we haven't yet detected. If dark energy weakens, the universe's fate shifts. Gravity might eventually overcome the acceleration, halting expansion and perhaps triggering collapse. The Big Crunch becomes possible again, a mirror image of the Big Bang where everything falls back together into increasing density and heat. If dark energy strengthens, the outcome grows more dramatic. Acceleration would increase not just in overall rate, but in intensity. This scenario, sometimes called phantom energy, leads to what cosmologists term the Big Rip. In a Big Rip scenario, acceleration becomes so powerful that it eventually overcomes not just the gravity-binding galaxy clusters, but the gravity-holding galaxies together, then solar systems, then planets, and finally atoms themselves. Everything tears apart at the fundamental level. The universe doesn't just expand, it shreds itself. The timescale for a Big Rip, if it occurs at all, depends on how rapidly dark energy strengthens. Some models place it tens of billions of years away. Others suggest hundreds of billions. Current measurements show no evidence that dark energy is strengthening, but we've only been observing for a cosmic instant. Beyond dark energy's behavior, other uncertainties exist. Our understanding of physics comes from experiments and observations in a limited range of conditions. We've never observed matter at the densities inside neutron stars' cores, never tested quantum mechanics across cosmic distances, never explored how gravity behaves over trillion-year timescales. New physics might emerge at extremes we haven't yet encountered. Perhaps protons don't decay, making the timelines we've described incorrect. Perhaps black holes don't evaporate exactly as Hawking predicted. Perhaps quantum effects we don't currently understand prevent the universe from reaching true heat death. Some theories suggest the universe might be cyclic, alternating between expansion and contraction in an eternal pattern. Each cycle could begin with something like a Big Bang, expand for trillions of years, then contract back into a dense state that triggers the next cycle. Our universe might be one of countless iterations in a chain extending infinitely into the past and future. Other theories invoke quantum fluctuations even in the empty universe of the far future. Given infinite time, quantum mechanics predicts that random fluctuations could occasionally create particles, even entire structures, from apparently empty space. These fluctuations might be rare beyond imagining, but in an infinite future, even the rarest events occur eventually. We don't know which, if any, of these possibilities represents reality. We've traced a single path based on our current best understanding, but that understanding is incomplete. The universe has surprised us before. The discovery of acceleration itself upended decades of confident predictions. Future discoveries could reshape our view just as dramatically. What we do know is that we live in a remarkable time, an epoch when stars shine in countless galaxies, when the cosmic microwave background bathes space in detectable radiation, when the evidence of the Big Bang and the universe's expansion lie open to observation. This era won't last. In the deep future, as we've seen, observers would find themselves in darkness, isolated, surrounded by a void that reveals nothing of cosmic history. They would lack the evidence we take for granted, the galactic light and ancient radiation that tell us where we came from and where we're going. We exist in what might be called the universe's luminous age, neither too early nor too late. Too early, and atoms hadn't yet formed, stars hadn't ignited, complexity hadn't emerged. Too late, and the lights will have gone out, the evidence erased by expansion and time. This timing is not coincidence exactly, but it's not random either. We're here now because this is when conditions allow for complexity. Stars forge the heavy elements necessary for planets and life. Galaxies provide stable environments where solar systems can form. The universe has cooled enough for chemistry but hasn't yet faded into darkness. We're made of matter forged in stellar furnaces, scattered through space by supernova, gathered into planets orbiting later generation stars. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, all were created inside stars that lived and died before our sun formed. In a real sense, we're the universe examining itself, conscious arrangements of matter that arose through natural processes, now contemplating the cosmos that created us. We can trace our origins back to the Big Bang, forward to a far future we'll never see. We can measure the expansion of space, detect radiation from the universe's infancy, predict the fate of galaxies trillions of years hence. This ability to understand represents something rare and perhaps fleeting in cosmic terms. Consciousness, intelligence, curiosity. These emerged from matter under the right conditions. Those conditions won't last forever. In the cold darkness of the far future, they may not exist at all. So we find ourselves in this moment, this brief cosmic instant when the universe reveals itself, when light from distant galaxies reaches our telescopes, when the evidence of our origins and our destiny lies scattered across the sky, waiting to be read. The universe is headed toward emptiness and cold, toward isolation and silence. But right now, in this era, it's filled with light and structure and possibility. We're here to witness it, to understand it, to marvel at the fact that the cosmos became aware of itself through us. That awareness, that capacity for wonder, might be the rarest and most precious thing the universe has produced. A brief flowering of consciousness in an epoch when the conditions allowed for it, destined to fade like everything else as expansion carries on into the deep future. But for now, We're here, and the universe spreads out before us, vast and ancient and beautiful, its past written in light, its future sketched in mathematics, its present moment ours to explore and understand.